This meeting is being recorded.
Welcome to Go Seminar. The first speaker of this semester is Jocelyn Thiebaut, and he will speak about approximation hardness of geodetic sets.
So thank you. Dobrý den, everyone. So this is a joint work with Tom Daho, Luca Isman. So Tom is postdoctoral fellow in Compiègne, and Luca Isman is a teacher assistant in Montpellier. And this is me for the people I didn't have the pleasure to meet yet. So hi. And this is my office if you want to say hi. I'm here. So the content of this talk is based on the paper we presented in Cocoon last year. We're about to submit journal version of this paper, probably this week. I don't know why I said probably, because I mean the deadline is tomorrow, so it's definitely this week. And yeah, so we're gonna start with some. Oh yeah, maybe I should mention this. So most of the base these slides are based on the one said by Tom for the conference. So even if he's not here, I want to thank him. So let's start with some definitions. So geodetic set. You take a graph. A geodetic set, sorry, is a subset of vertices such that if you take the set of the shortest path between those vertices, you cover every vertex of the graph. So very important here, if you take those two vertices, you take the short path between those two vertices, and you will end up with those two. You will cover all those green vertices, and you didn't cover everything, so you need an extra vertex, for example, this one, and that will cover all the graph. So if at some point you miss something or definition, if I'm not here, feel free to interrupt. So we're going to call, of course, we want the smallest one, and we call like this, the size of the smallest geodetic set of the graph. So here are some examples of on some classes of graph. So for example, on trees, one important thing is that it's easy to understand that you need to take leads. If you have a vertex with degree 1, you need to take it, because otherwise there is no other way to cover this vertex. So you need to take all the leaves on the tree, and in fact, it's enough. It's easy to see that it's enough on trees to take the leaves. For complete graphs, you have to take all the vertices. You have no other choice, because the shortest path is the edge between the two vertices. So you need to take all the graph. For grids, it's a little bit more trickier, but it's still easy. You just have to take, like, for example, the opposite corners, and you cover all the vertices by the choose M path, shortest path between them. And for bipartite graphs, complete bipartite graphs, sorry, here you need to at least have two. Okay, if one of the part is small, you take all the vertices of this part, and if not, you just have to take two vertices of each size, and you will cover all. Like for example, if you take those two vertices, you cover all the other vertices by the shortest path between those two vertices. Okay, so we will talk also about the strong version of this poem, namely strong geodetic sets. It's basically the same, except that you can't take all the shortest paths. You have to pick one of them. So for example, here we come back to our previous example. Here at the beginning we took those two vertices, and here we have to choose if we take the green path or the blue shortest path. So here, say we take the green one, we need an extra vertex. Here with those two pairs, you have this shortest path. You have several choices, in fact, but we can say you take this one. Same for the other. You need another vertex, and here you cover everything, all the vertices. So, and similarly, you want the smallest subset of vertices that satisfy this property. So let's come back with our examples, just way faster, not to spend too much time on these. For the trees, it's the same. Same for the click. For the grid, it's a little bit more trickier. You need to take the first row of the smallest, the first row of the first column, depending on the smallest, and one vertex of the last one. And for complete bipartite graphs, it's known, but the formula is very much complicated. Okay, so for definitions and more variants of this problem, basically it's the edge version of the two problems. That is, now instead of wanting to cover vertices, you want to cover edges. And of course, so the first one is called edge geodetic set, and the second one is strong edge geodetic set, and it's the same than before. You have to choose one shortest path between every pair of vertices of the subset. So some results around what I will present you here. So all those problems are in T-hard. Historically, the first problem that came was the vertex version. It was proved hard in 1993, and I think this problem at the base was similar to a game theory problem where there were two players that had to pick one vertex, and it had all the shortest paths between the vertex already chosen, but I don't want to confuse you with another variant of this problem. Another result I want to mention is that geodetic number is LOG-APX-hard. And I want to mention it because one of our results is to prove that edge geodetic number is also LOG-APX-hard, even of subcubic bipartite graphs. And to do so, we do reduction from set cover. So just a quick reminder, you have a collections of finite sets, C, and you over a universe of elements, E1 to E1 and so on. And you want to find the smallest subset of those sets, such that every element is covered, is contained in the set of you want, of course, to find the smallest one. So how the reduction works. So let's take this super instance of set cover. And for every set, you will create a path of the three vertices here, like this. And for every edge, for every element, sorry, you create a path of four vertices. And now, for the second vertex of the blue path, the element path, you will connect them all together. Like it's not obvious, but it's a click. It is a click, of course, but it's not obvious here. So you connect them all together, and finally you connect a set to an element. If an element is in the set, like E1 is in S1, you connect the last vertex like this in green. It's obvious that it's green, but whatever. And the vertex just before like this. So in total, you'll have this graph. So of course here it's not a super hard example. I mean, this is planar, but there is absolutely no reason to be planar, especially with the click. So as I said previously, we know that we need to take all the leaves. So let's take them and just check what do we cover, what edge do we cover just by taking those edges. So let's consider the case where we have two elements, two distinct elements. So let's consider what covers the shortest path between the leaves corresponding to those elements. So here in blue, the top blue, here, this vertex and this vertex. So the shortest path here, it's pretty obvious. It goes through the edge of the click, so distance 3. And in total, if we do all this reasoning with all the pairs of distinct elements, we'll cover all these edges. Now let's consider the case where you have a set Si and an element of this set. So for example, with S1 and E1. So in that case, the shortest path is also obvious. And I guess it's distance 6. 1, 2, 3, 4, 5, 6. Yes. And it's the unique shortest path. So in total, we will cover basically everything except the edge of the click, but it's already covered. And the last this row here. Now, if we consider the case of a set, an element not in the set, so with this leaf and this leaf, like E2 and S1, we'll use, basically, we won't go through these edges here because the edges of the clique is way faster. And in total, we cover everything, but almost everything except the last thing here. And one more, there are two cases remaining, so it's almost over. The case of two sets that share an element, then there are two possibilities, either this path, I guess it's distance 7, if I remember well, or this one. I put it on another pair of sets just to make it more obvious. So here, and this is better because we cover the last row that is way more interesting for us because it's not covered so far. And in total, we have covered this. And finally, last case, between two sets that does not share any element. Here, basically, they are too far from each other. So one more time, we need to take an edge of the clique to find the shortest path. In the case, it's distance 11. So if we sum up everything, we realize that almost all the edges are already covered. And in fact, the only edges that are not covered by the leaves that we need to take are those, the last edge of the blue path. This is the only thing that is not covered. And in fact, we can prove, it's not super hard, I will give you some intuition of it, but it's not to prove that if we have a short path that covers this edge, then at least one of its extremities is not far from here, from the edge. And in fact, the idea is just to say, if both extremities for which the shortest path covers this are too far, if both extremities are far, then it's better to take the edge of the clique. And with this idea that extremities are not too far, then we can prove that we can restructure the solution to take instead, for example, this vertex, the last vertex of the set of the set path. And for example, here, if we take S2, this vertex, and we consider the shortest path with this element, then it will cover the edge as we will want it. And in fact, it will also cover the other edge. And we can see that now, by taking S2 as in 4, we cover all the three edges. And it shows you, I mean, the idea is that S2 and S4 is a set cover of our instance. And in general, we can say that S2, S4 is a set cover if and only the set of leaves plus the blue vertices is a geodetic. And also that if you have a set cover of size k, then in the graph resulting of this prediction, you'll have a geodetic number of u plus c plus k. And using this, now suppose you have a polynomial-time algorithm that approximates a geodetic number, and you take an instance of set cover, you compute in polynomial-time the prediction I just described. And then you'll have this equality, that is the approximate version of geodesic will have the same property as before. And it's, in fact, it's also the same for the optimal solution. So what's important now is the ratio of these two things. And in fact, like this, it does not work. Importantly, the parameters here is this additive constant, additive value, sorry. And the idea to solve this problem is to create copies of the graph we just made. So these are not like aliens with weird glasses. It's the copies of the graph. So you have two copies. And here I depicted this way because you have the graph. And here I just put outside of the graph the leaves of the graph. And so the leaves. And we know that if we take those leaves, we cover almost everything. We just have to solve the set cover inside each copy. So now what we'll do is for each leaf, we'll create a copy of the leaf, and we'll connect them like the red with the red and the blue with the blue. And similarly as before, if we take those leads that we have to take, we'll cover almost everything. And we'll still have to cover to solve step code in each topic. So, and this we can do it with as many copies as we want. So if we have k copies, we'll end up with a k constant, k factor p. So when k tends to infinity, it proves that the approximation, it proves that we have this equality, and since set cover is LOG-APX-hard, it proves what we want. But there's a but. I've told you that it's LOG-APX-hard on subcubic bipartite graphs, and this is everything but subcubic bipartite graph. So we need to solve a little bit of things. The bipartite part is not super hard because all you can do is to take every edge and subdivide it. So it will make your graph bipartite for sure. But the subcubic part is a little bit more tricky. I will give you some hints of how to do it. So basically, it's that if you have a vertex with high degree, you will make it like a binary. It's not really binary tree, but you make this tree out of it, where every vertex has degree as degree. And the only thing you have to be careful is just not to mess up with the distances too much. So, but there are several ways to do it. So it concludes proof. And the good news is that this proof can be adapted for geodesic numbers. It's pretty easy. However, the whole construction I just presented you doesn't work for strong geodetic number, and it's pretty easy to see because we'll use the same shortest path again, several shortest paths again. So it's not working. However, if you remove the copy part, okay, maybe I should stop here. If you remove the copy part, the reduction works on strong geodetic, and we can use this reduction to prove that there is that's hard to approximate with this factor better than this ratio. So now, okay, so now all I've said, all the construction, you can just forget it. You can garbage collector this, just to free your mind a bit. So now an interesting question is the following. So you have a graph, and you have subset of vertices. So in the strong version, you have two things to do, basically. You have to find the subset of vertices, first step. Second step, you have to pick the shortest path for each pair of these vertices. Here, we prove that, in fact, just the second step, if I give you the subset, just the second step is hard for strong geodetic. And we did this with a reduction from a variant of SAT. So since it's hard to find an assignment of shortest path, a natural question is to cover as many vertices as possible. And this is the problem for max-heuristic assignments, where it's exactly what it said. You take a graph and a subset of vertices, so you don't have to find this. It's done. And you have to cover. You have to find which shortest paths cover that cover as many vertices as possible. For this problem, it's broken. Oh no, it's me. I'll turn it off. So for this problem, we have this simple greedy algorithm. Basically, you take the set of vertices, you consider all the pairs of this set, and you take those pairs one after the other. And every time you take the shortest path between this pair, that maximize this, and this is just basically to say that maximize the vertices that are not covered. So you take the best choice all the time, and you set this shortest path every time. And this algorithm is a true approximation of the problem. I'm going to give you the proof of this. So you take the assignment returned by the algorithm, we call it A. O is the optimal solution of the problem. And the goal is to build a function between the vertices covered by the optimal solution to the vertices covered by the algorithm, such that there is no vertex of the approximation. There is no vertex covered by the approximation solution that is touched. I'm going to say this way twice by a vertex touched by covered by the optimal solution. And because if this is true, then it means that the size of A is less than 2 times the size of the optimal, which is exactly what we want to prove.
Error.
Sorry?
The size of the optimum is at most twice the size of A.
Yeah, sorry. No, I said the size of the approximate solution is less than 2 times the size of the optimal. I don't know what I said.
But the approximate solution is smaller than the optimal solution, isn't it?
The approximate solution is more. It's bigger.
Yeah, you have more vertices.
You want to minimize the number of vertices. You want to oh, sorry. Oh, yeah. Sorry. Yeah. Okay. Sorry. No, you're right. Then so yeah, it's the opposite. Yeah, it's.
Because we are trying to maximize the number of vertices covered.
Yeah. Sorry. Yeah, you're right. I'm sorry. So first thing, I get confused with all these variants. So first, if you have a vertex that is covered by both solutions, you take you set F as the identity of those vertices. Second, you consider you call PIA the shortest path chosen at step I, and the PIO is the shortest path with the same extremity than this one, but in the optimal solution. And you call AI. Okay, this is just a way to say the vertex that is covered by the new path on step I and never covered before, and same for OI. And you know that this set here cannot be too big, because if it wasn't the case, if it was bigger than AI, then we wouldn't have chose PIA in the algorithm, because every time we choose the best one among all the possibilities, among all the short spots. So it means that there is an injective function GI between those two sets. And what it means now is that for every step, we set the f of b equals to GI of b. So now we have this function, and we want to prove it. We want to prove that it has the property we wanted. So you take a vertex of covered by the approximation algorithm, and one thing we can say is that there is at most one vertex that has image U by F of this set. Why? Because on this set, F is defined as the identity. So if there were two, there would be the same vertex. Second remark is that at any step, they can't have more than one vertex like this of this set with the image by F that is U. And here it's because we picked GI to be injective, so there were two, it would be the same vertex. And finally, they cannot have more than one step such that you have this. And here the idea is that because AI is a partition of A, so if there were two, it would mean that it's not possible because it's a partition. So in total, we have what we wanted, which proved the ratio. And we can prove easily that the ratio is tight. And the idea here is to find, like we have this example where the ratio is tight. Consider you have this graph, and I give you these three vertices. The optimal solution would go from the pair AE to go through B, and then from the other we don't have many choices, so we cover B and D. However, in the algorithm, if at the first step we fail, like if when we consider first AE, we go for D, then it will be impossible to cover B. So we covered one vertex instead of two in the optimal solution, which would be ratio. So final things. So there were a conjecture that was about the fact that a strong geodetic set is NP-hard in complete multipartite graphs, and we proved that it's not the case. And we gave an algorithm in we go to the n to the 8 in that solved the problem in this class of graphs. And the idea here is to use dynamic programming. So finally, let's put some words of conclusions. So we proved that it was LOG-APX-hard. I think a natural question is that, okay, it's hard now. Can we reach this approximation ratio? I don't have like strong feelings about this, like if it's true or no. It may be true, but it's just intuition in this concept of nothing. I don't know why I said that. It's worth nothing. Anyway, okay. So we also proved that it was NP-hard to know if a given set was a strong geodesic set of graph, and now we can ask ourselves if it's true for the edge version of the problem. And finally, we gave this algorithm in complete multipartite graphs, and I mean, it seems fair to think that it may be possible to do better than this, which was absolutely not the idea of this algorithm at first. But we probably can do better than this, and we can consider also other classes of graph when maybe it's polynomial times solvable. And I guess, of course, we can look for parameterized complexity too. I don't think, maybe I'm wrong, but I don't think it has been studied in parameterized complexity area. But maybe it would work to take a look at this. So thank you for your attention.
Question, comments?
Drink. No questions.
Can I ask a trivial question?
Oh.
So going back to the approximation algorithm, instead we take the shortest path that maximizes the number of vertices that are not yet covered. So
Yes.
how exactly do you do this? I don't see it.
You can compute the shortest path, all the shortest paths.
So that's exponential manner.
No, I think you just do
Well, you can count how many there are, but if you have to look at every shortest path and count before them, right?
You can do some other programming function.
Yeah.
Set breakpoint for covered vertices and 0 for uncovered. Then you can start this.
Not too late, but we just keep the best out of this. That's basically like not but
Yeah, we should mention it. Okay. Yeah. Sorry. Yeah.
Okay.
This seems to be related somehow to metric dimension, where there are some results in parameterized complexity. But I know these relations are always like, there is some relation, but not really.
Yeah, there are a lot of again. It's okay. Metric dimension. The idea to maybe for people who doesn't know it. So you have maybe I won't explain it like the best way. So you have a graph and you have to select a subset of vertices of the graph such that if you compute the code between this for every vertex you compute the code that corresponds to the distance from this vertex to all the vertices of the subset you took. and you want this code to be unique, like to be able to identify this vertex among all the others. I don't know if it was clear. I don't think it was. So yes, there are a lot of problems of identifying vertices in graphs. There's also identifying codes, and another one that I don't remember.
Yeah,
Maybe there are like gaps, bridges between them. Yeah, I don't
maybe
know.
not. Yes.
I don't think I answered your questions using one.
I'm not sure that I had a question. Okay, any further questions? Right. If not, then let's think again.